Okay, we are live. Hello, everyone. Good afternoon. Is everyone listening to me well? Let me see if we have anyone in the chat. Okay. Okay. Thank you. Okay. Hello, everyone. Good afternoon. Welcome to our first USA webinar. Thank you very much for joining us today. My name is Vini. I will be your host for this session. Please feel free to send us any question on the chat. We will reserve a few minutes to read and answer them in the end of our presentation. So today we are going to talk about the power of simulation and AI for stamping defects detection, including one of our main products, Autaza Surface, which since last year we have received several updates, including new features. And to talk about manufacturing tools and stamping simulation, we have two special guests, Isadora Coelho, our software manager. She's going to present all the newest features and explain in details how our solution works. And Arthur Camanho, he is the Smart Manufacturing Director at ESI Group. For those who still don't know, Autaza and ESI have a development and distribution partnership for a few years now. So Arthur, thanks for joining us today. Please give us a brief introduction about yourself and what is your role at ESI.
Thank you, Vinny. Thanks a lot for opening the webinar. So my name is Arthur Camanho. I'm talking to you today from Michigan. That's where I'm based today. I'm working now with ESI since 21 years, mainly with manufacturing simulation. And lately, I'm the director, the global director for Smart Manufacturing Solutions. So I'm on defining the strategy and working globally with our solutions towards manufacturing, which are casting, welding, assembly, composites, and stamping. So thank you very much for joining. I'll start by explaining a bit how we met each other, how we met with Autaza, and why this partnership makes so much sense for ESI. So at ESI, we have what we call a ESI VM suite. It's a virtual manufacturing suite that has all these softwares and all these solutions that I talked about. These solutions are mainly on casting, composites, stamping, line dies, and assembly. And Autaza is the perfect fit for our line die solution and also for the assembly distortion engineering solution. That's why we talked a lot in the past, and finally we have an agreement since some years and developing our solutions side by side. In terms of opportunities in the automotive industry, Autaza is quite known for analyzing parts in the shop floor, right? They look at stamped parts, they look at the body shop after assembly, and then finally the body in white. What we're trying to add to that is the simulation world. Okay, what do we do before that? So ESI is all about simulation since almost 40 years. We do simulation of all that, so stamping, assembly, and this makes a lot of sense for us to look at surface quality of parts, right? Still in the simulation world. Here you see a single part. So in this case, we're talking about sheet metal forming. But as I said before, not only that, we also use the solution to look at assembled parts, right? When you have a door which is assembled, when you have a hood, after assembly, you may have new defects, and that's a perfect way for us to check if there is a defect or not, and if there is a new defect after assembly. So how did we start that? At ESI, on our side, we had to develop what we call a virtual light room, right? You see here on this picture, this is pretty much the way people look at surface defects in the shop floor today. This has been like that for many, many years. You have a specialist looking at a part against a wall or against a tunnel of lights. And by looking at the lights, this professional, he has a feeling, he knows there is a defect, and he can even rate himself that defect. And he makes a few notes on those parts, right? So we had first to be able to have the same in our environment, right? So we developed a virtual inspection room. We call it, as I said, the virtual light room. So the first challenge was to have that high quality of rendering and surface details in the virtual environment, so we could check those defects in the virtual environment. If we could not see the parts and defects with clarity, with realism, it would be almost impossible to rate anything or to check any surface defect, even with the help of Autaza. So that was our first challenge. Even when we completed that, right, this is a picture of a door in our virtual light room. You see, this is not a picture, it's a real simulation result. So this part was simulated in PAMstamp and it went to the Lightroom. And then you see possible areas of defects, but it was still tricky and difficult for us to measure the defects. Okay, is that defect visible? Is that a real issue after painting the body? That was really a gap we still had with the market that was telling us, okay, you have a great way to visualize a surface, lights, but how do you measure defects, right? How do you tell me if these defects are low, medium, high severity? That was still difficult. So the workflow to answer to that was today we start from, as I said, from simulation. So this is a fender that was simulated with PAMstamp. Then we have our Lightroom that was developed, as I explained before. And finally, you have now in the picture, you have Autaza Surface, which is analyzing this surface and these light fringes, which are a result from the virtual Lightroom, and it's using artificial intelligence to tell me the severity of defects. If there are defects, and if it's a positive answer, which is the severity of those defects. So this is a quite unique way to still in the virtual environment to spot defects and spot even the severity of those defects. So a little more details about how do we capture defects? What do we do precisely not to miss any defects? You see again a region of a part, a door, which is being analyzed, and then you have a source of light, which is positioned accordingly to standards from Autaza, and then in this source of light, it's going to show fringes, light fringes on the part. So this is the real reflection of those lights, and the way we ensure that we capture all the defects is by using 2 vertical fringe patterns and 2 horizontal fringe patterns. So You have a first horizontal vertical pattern, and then there is a small translation in between these two patterns to make sure we are not missing a defect which is in between two lights. And then the same for horizontal fringe patterns. And all those four images are analyzed together with the artificial intelligence engine to get the severity. Finally, that's the main target. So I'll hand it now to Isadora. Isadora is going to explain you what is behind. Okay.
Hi everyone. So I'll talk about Autaza methodology and Autaza Surface system that we use to read the subjectivity of defects detection and classification. So Autaza methodology uses images or 3D data to form a database and learn from this data to create an algorithm to know those patterns and give the features and aspects of the defects that are important and the same features that the inspector looks for when they're searching for defects in a part. The algorithm in the middle here, the input goes through several treatments and processes to give us those efficient features that express those real world features that we see in the Lightroom that Arthur just showed us. So in the end of our methodology, we have an intelligent report that is free of that subjectivity and gives us an answer of what to do if it's a defect and what's the action to take if we have to rework or not. So let's move to some real examples of defects. Those are defects that we see in a real stamped part. Small defects most of the time, and in the images we can see that they are apparently harmless defects, but in the virtual environments that we saw Arthur showing, we have a simulation of a painted part. So we have the visibility is enhanced, and it's the same visibility that we have of a painted part. So we enhance those defects and analyze them as they would be in a painted part. So it's the aspect that we're gonna have in the final car, in the final part in a car. So moving to more specific details about the system in Autaza Surface newest release, version 11. The most important features and expected ones are the ones in the 3D environment, where we have the 3D curvature, profile extraction. We can move to one environment to another now that we have those two different analyses involved. The 2D feature in this version is an option for us to inspect an entire part and save and export all the inspection reports all at once. Talking about the environments, the user can go from one to another and move along the analysis where while we evolve in the analysis that I'm going to show you in detail. Here we see the user interface. It's pretty simple. Even though we have some valuable analysis here performed, but we leave everything to the computer and the adjustments that the user needs to do, they are just a few and only if necessary. And we have, in most cases here, an analysis with one click. Just going to the 3D curvature, we can see a part analyzed, the surface analyzed, and shown to us as a heat map. So we have the surface behavior expressed in those colors. We have the positive values that we can set in the parameters, and the blue colors express the negative values. So we know how the surface is behaving. And the green one, as we see in the label, show us the planar regions. So it's pretty simple to analyze, to see the to look at the surface and find those defective areas, so we can move to the other analysis. This is a moment where we also can use the CAD file, the design of the part, to know how was the expected appearance of that surface, the designed appearance. And here we have a simulated part where we see that the curvature, I don't know if you can see my mouse pointer, but along the arch of the part, we were supposed to see the same curvature going all along this arch. So this is where we are going to show you some real examples. Going back a little bit, in this analysis, we also can configure the most important parameter here is the search radius. This parameter can give us in an abstract way how zoomed in we are in our analysis. So if I configure here a smaller value, it means I'm looking a little bit closer, I'm looking to a smaller defect. And if I configure a higher value, for example, I can ignore those small defects and look for the bigger ones. So what is I talked a little bit about how the surface is supposed to behave, but what is that exactly? Here I have some examples of clean areas, the areas that I don't need to worry about, and I don't need to focus in the other steps, the next steps. And in the right side, I have some irregular areas. I know that the area I'm looking at wasn't supposed to have this subtle change in the curvature. So this is a point where I have to analyze and move to the other tools that we have in Autaza Surface. So being more specific, when we select the regions that we need to focus on, we can move to the profile extraction. In this feature, we can see how the surface in a 2D profile, how the area is behaving. So again, a very simple feature. Everyone that already used a feature similar to this one in a 3D software will be surprised by how fast it is and how simple it is to use. So here with 2 clicks, I can export the profile of the region in several formats so that I can analyze in other softwares if necessary, or include it in a report, for example, as an image. Just zooming in the graph, it's pretty simple to analyze. I can even see some features like height and length of the region that I'm looking at. And so the magic here is this case where I'm looking at the curvature, and I can extract the profile above this heat map. So I have the heat map as an input for me to choose the points to analyze. So here what I did was following the curvature line that I was talking about. Here I was supposed to have the same curvature going along this line here, and I chose some profile areas to analyze. And I can see two examples, one of a defective area that I identified in the heat map, and a second one where I have a clean area, and I can see the difference between them, okay? So this is the answer that we have using the 3D curvature and then the profile extraction in the defective areas that I identified. Here a closer look in the graph, and I can see the difference among those two regions. Well, what we did here, it seems like it already gives us the answer about the defective region, but I still have to have the final answer. Is it a defect? Is it something that I need to worry about? So this is what the 2D environment gives us. So this different analysis that expresses some optical phenomena that is important for us to give the final answer that we talked about. So this is where we have the answer that is it something I need to worry about. In the 3D environment, we had some features of the surface being analyzed. So we have even geometry and feature lines, defects as well, but not just the answer we want, which is about the defects. So we go from that profile extraction to a 2D analysis of that same area. Arthur already showed us a little bit about the zebra lines that we have in the 2D environment, the virtual environment. And here I also have some features of the defects being shown in the fringes. We reflect the lights in the surfaces, and we can see the defective areas. Oops. In the first one, we see a very severe defect, and the middle one is the fender that we were looking at. So we see the waviness defect here. And the third one, a door, we see a more subtle defect. And so in this environment, we're looking at the part and we're extracting the features that the inspector can also see when they are in the Lightroom, the real Lightroom, inspecting a physical part. And remembering that we're in the simulation steps here, right? So we have the same aspect, but in a simulated part. This is a case that can illustrate what the 2D analysis gives us as an answer. So I start with the virtual mesh, moved to the 3D analysis, to the 3D curvature, to have a more general perspective of the mesh of the part. So I can choose some points that I want to have a closer look. And the next step, logical step for our analysis is to move to the profile extraction. This is an example where the 3D curvature showed something and in the behavior in the heat map. And then we moved to the profile and we saw the defect there, a very small change here in the graph. And then we want to know if this is something we need to worry about. Is this something that the final customer would be able to see in a painted part in a car? So this is the final answer that the 2D analysis gives us. The fringes here are clear, no defect detection. So this is something that won't be a problem in the future, won't be a defect. Okay, so this is a different aspect that is shown in the 2D analysis. A closer look of this case. So I have the profile showing the difference in the surface, the curvature as well, but the 2D analysis gives us the final answer, which is not, this is not a defect that I need to worry about. Now Arthur is going to move on to some surface analysis as well.
So the first question we get, I think, when we present this solution and some of the results is, was it validated? Does it make sense? Results can you trust results? And for that we have this one example here, but there are many. This is a real part from an OEM. This part was analyzed by the inspector, as I explained in the very beginning. The light, the inspector is in front of a light wall, or in a light room, and then he takes notes of the defects. You see small circles that are defining where the defects are, and then the inspector also gives a grade for those defects. And of course, we took, in this case, we took the same exact case, still from simulation. Okay, so that was not yet, the mesh that was analyzed was coming from simulation, was not coming from a scanning, the scan of the real part. Okay, we did that as well because we want to make sure that the scan of the real part is also captured. The defects are captured by the system, of course. But in this case, it was we wanted to go to the most difficult one, which was, can we simulate the forming of this panel, and can we predict the issues even before this panel exists, right? And you see here it matches extremely well to the real evaluation done by the inspector. Some other question that we get often is where we can apply the system, and as we said here during the presentation, in this case, the use case, the most often used case is the stamping simulation result for single parts. So you have this case a door outer, or you have a hood outer, or and then you look at surface defects. In this way, Isadora was showing that you can use the curvature to take a heat map and to find the hot areas where you can get results, bad results, and then you go for the 2D inspection with the light, and you measure those defects. Are they really visible? Not only that, as in the very beginning I said, assembly was also a hot topic. When this door is assembled, or when parts are assembled, many things happen, as you know very well, and you may have new defects. Okay, so it's a great way for us to understand if the defects are coming from stamping, from assembly, or even in stamping. Is it coming from forming? Is it coming from flanging? Is it coming from hemming? So we can analyze the parts. You pick points on the parts, and you analyze those points after forming, then after flanging, and after hemming. And then this gives you a very good idea of what needs to be fixed, right? Sometimes if you just look at the final part, you may find a defect, but it's not very obvious where the defect is coming from. Also put here that the system is a great tool to analyze die faces, right? Before stamping a part, even for simulation, you have a die face, right? And the die face is created based on the part CAD. And sometimes you may have surface defects when you create a die face as a result of the die face creation or as a result of the die face morphing, right? If you need to morph your die face to control a spring back to do some kind of compensation, you may have introduced some surface defects. So it's a great way to check if the die face looks okay. And finally, or actually in the very beginning, ideally, you want to look at your part geometry. Okay, we've seen cases where the part geometry received from the studio was showing some small defects, and these small defects were shown in the stamped part. So you can use this additional tool on top of the tools which are already used by the studio. Maybe there was some issue in conversion, maybe there was a small issue that was overseen by the surface designer, and you can capture that. So you try to capture the part. The part is normally okay, but not always. Then you go to the die face. When die face is okay, you can do stamping, and then you find defects which are process related. And then finally you go for assembly. So you can cover all those steps with the solution. So with that, I think we covered most of the information we want to give today. I hand it back to Vinny. Thanks again, and we are open for questions or whatever information might be needed.
Okay, thanks Arthur, thanks Isadora for the presentation. It was very explanatory. I will give more minutes if anyone wants to send us some questions. But in the meanwhile, I will thanks everyone for joining us today. Please take a look at our social medias on the screen. We have our website, which we have new pages, and we have a new center of inspection in São José dos Campos here in Brazil. Also our LinkedIn page, Facebook, and Instagram. If anyone has any question or if anyone wants to know more about our products, please write to us. Our contacts are on the screen. Also, Arthur's contact is on the screen as well. So have a great day, everyone, and stay safe.